All right. In this section, we're going to be discussing the implementation of the current loop, specifically output current to duty cycle. Well, that's what we used to obtain the coefficients in this case, but specifically in this section, we'll be focusing on um, implementing closed loop control, but specifically controlling the output current of the buck converter. Um, Before we actually start with that, um, I sort of want to go into changing the set point because that was one of the goals here for sort of robustness. So I'm going to change the set point in this case to something like 10 volts to actually see the results to ensure that the actually implementation of there's an implementation of closed loop control on the voltage. Okay. I'm gonna have to switch views. I'm gonna have to switch views now. Okay, try again. And I'll just turn on the LED. Well, the purpose of turning on the flash, of course, is to be able to see the frequency. Um, Not the frequency, output the output average voltage, which is right here. It's not visible if the flash is off, so it shines in the corner of the screen, but actually it's better if it's on to actually see the readings on the oscilloscope. Alright, so it's been loaded, the code's been loaded. I'm gonna turn on the converter. Okay, there you see it's about 11.5. Due to the 1 volt offset, this should be somewhere around 10.2 volts, thereabout. Um, but as you can see, the voltage on the actual output voltage is 10.42, which is of course almost a voltage less than 11.5. And thinking of course there's a slight offset there to what we set up in the code, which is 10 volts. Um, in essence, how to deal with this is basically to increase to average more, basically to average the voltage more, to use a more precise voltage sensor, which of course will affect the loop. So you'll have to incorporate this into the loop design. Or another thing that you could do is simply adjust the reference, the VREF, make it slightly lower. Understanding that there's always going to be sort of an offset in your output. Just find out that average offset value and actually change it. But personally, in most of the applications that I utilize, um, you do want it to be in a certain range. So for example, if you choose an output voltage set point of 3.3, you want it to be about 3.3 to 3.5, thereabout, and you sort of want it to be in a certain range. And it's important to note there are a lot of factors to actually get it to be exactly 10 volts, which you require. But most of the time, what you would actually get is something that's in the range that you would like, not exactly bang on, and to the exact voltage that you require. But anyway, that's that. So now I'm gonna pivot into the output current output current control, which is the next part of this. So I'm just gonna turn that off. This point, it's not required anymore, and I'm gonna switch views now. All right, so we're back to the firmware, and yeah, that's about that. So I'm gonna switch on to the current section now. As you can imagine, the main difference here is basically the use of the current control coefficients that have been calculated earlier on. So first off, I'm gonna go to the custom.c um and create one for the current. small letters. And I'm literally gonna go to the custom.c. Well, that's a custom.h. Then go to custom.c and create one exactly like this. I'm just gonna say current there. All right, so the first step, of course, would be to calculate the I actual, which is this, which has already been done. So I'm just gonna go back and change that to I actual. Don't forget the array element, which is 1, or ADC values. And of course, this is going to be changed to I, oh, not capital I, I, I. I don't know about you, but I prefer, this is a much quicker way for me to just, change these values as such. So IRF and I actual, and change the I values there as well. I, I, I. I over there. I. I. Basically, everywhere there's a V, you just change that to I. Same down here. I. Of course, everything that needs to be defined will be defined above I. And what you want in the end, you want to change that to I. All right. And also, because we're checking the I actual, there isn't a presence of a current sensor here, so it will still be the voltage that will be measured across the output resistor, but the resistor value is 7.5. And if I calculate 7.5 times 2.133, that's about 16. So we should see an output of about same thing, about 16 point something on the output. So yeah, that's what we should get. All right. Let me just modify this. And secondly, what I also wanted to state, just a quick sort of side step here, is the for to get more accurate output voltage values for your set point actually has a lot to do with the resistors that are chosen as well. Because in the calculations, I'm assuming the values of the resistances are 910K and 100K. So basically what that means is it's better, I'm using 5% SMD resistors. So in these cases, it's better to utilize 1% resistors because they give much more accurate results. So you should utilize those instead of 5% resistors, and you would get much more accurate values. It's just changing the offsets in the code or changing it according to what I see on the output is sort of going to be a mess. I sort of like to keep it kind of nice and tidy as with what I calculated. So in your applications, I encourage 1% using 1% resistors for output voltage sensor applications. Yeah. All right. That's that, and the max duty stays the same. All right, so now I have to go up and actually change the coefficients, but before you do that, you just need to make sure that everything, because I copy and pasted, you need to make sure everything is I, there's no V anywhere. It's gonna cause a mess. And of course, you can guess what I'm gonna do here. I'm just gonna copy that, and paste that there, and change this to an I, 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 and I. And do the same thing down here. Or you don't have to, you can have almost like a global output min, but for the sake of this example, I'm just gonna have one for yi. All right, and these coefficients, I'm going to go back to the document. So these are the coefficients that are calculated for the current. If you look up here, it's just scrolling down for the output current. So BO is this, and IO is this. And B1 rather is this. So, and the rest stays 0. So it's not even defined there because it's assumed that the rest are, well, basically 0. Okay, let's just go back to it, to the firmware. And in essence, that's about it. That's basically it. So all we have to do at this point is basically to call this function and see what happens. Let's go to main, and the interrupt, call this function. Of course, comment out the first one, and we don't need this anymore, so we just take that out. Yeah. Okay, let me just run it. See if there are any errors. Okay, 0 errors. That's always nice to see. It's fantastic. Alright, and the set point is 2.133. 2.133. Where is it defined? Yep, 2.133. The reference multiplied by the output impedance, which is approximately 7.5. So I have two 15 ohm resistors connected in parallel here. That's about 7.5, and the output and the output voltage I want to obtain in that case should be about 16 volts. So I should be expecting to see 16.0 to 16.5 on the output at this point. So I'm just gonna run it. I'll code into the system. Okay. So I'm writing it into it. All right, it's done. It's done its thing. Let me just change the view here, as it's important to see the results on the oscilloscope. Okay. Okay, flash on. All right, so I'm just gonna turn it on now. Okay, you get something similar. So should be about 16.5. All right, let me just measure the output. So it's measuring. So it's basically controlling the output current at this point. All right. As you can see there, the output value is 16.5. 16.5 volts. So what I'm gonna do now is I'm gonna change the set point to about 1 volts. Sorry, 1 amps. We should see an output voltage of about 8 volts to 7.5 volts at that point. All right. So first off, let me turn it off. So in the firmware, let me just change the set point. Now let's say 1.2. 1.2, because this is also designed to be robust. About. Alright, I'm gonna run this as well. So at this point, we should see an output. At this point, one should see an output voltage of about 9 volts. So I'm going to change the view again. Flash on. All right, let me just turn it on. Let's just offset a bit. Let's turn it on. All right, so it's about 10.9, which knowing the offset should be about 9 volts at this point, or 9.5 thereabout. And there we are. The voltage is about 9.62 volts, but it should be noted that the set point has been changed. The set point has been changed, and you can actually see that on the output. One thing specifically should be taken into account here, which is the fact that the resistor does change its resistance as a result of heat, i.e. the resistance actually goes up when it gets hotter, and that plays a role. That plays a huge role into this particular reading that we see here, because it's the voltage we are sensing for the oscilloscope. There isn't a current probe here. So basically, that's what you get. The output current control with the digital control coefficient utilized. All right. So let me just get back to the firmware. All right. So that's about it for current control. So that's basically all the work that has been done up to this point. In terms of determine everything has basically been to, let me go to that section of the code, is to obtain these coefficients. That's all that's really necessary here. Of course, you could thumb suck it, but wouldn't really, you could do that, but then again, you would have to start from a really low BO value, like something like that, just to be safe, as opposed to calculating exactly what you need and just implementing it, in the system. So that's sort of what you want to do. Yeah, there isn't much more to it. I'm trying to think of anything else to say regarding the closed loop current control and closed loop voltage control. But this is about it. Anyway, from the compensator standpoint, from the digital compensator standpoint, this is it. And the most important parts, of course, are actually, calculating the actual I actual value and the V actual values, and you wanna make sure those are correct, and you want to make sure you use precise values, especially for the voltage sensor. As you can see here, they're using 5% values. Does have an impact on the relationship between your set point and what you actually get on the output. It's important to take that into account. And that's about it. Well, there was something else specifically that I wanted to discuss, which is of course the how do you say um the current sensor. As you've noticed, as I explained, in this case, I like precise current control. um so I use the shunt in this instance, but obviously when you're going up in the current, when you have to sense like high current values, like I'm talking 15 amps and above, it's not advisable to use a shunt. The shunt changes color and things like that, and changes resistance at some point, and it affects the efficiency of your system. It just does, of your converter. So in certain cases, you want to utilize a Hall effect current sensor. They're much better. They're much more, and they're high efficiency as well because the resistance is almost negligible. So in that case, this equation will not suffice. Let me just zoom in a bit there. This particular equation for I actual will not suffice. So let me just explain how you would modify this equation in the case of using a Hall effect current sensor. All right, so a Hall effect current sensor essentially works with offsets. It usually has an offset value and a sensitivity. I'd explain using the STM32 current sensor. I'm not sure if you're familiar with it. I'm sure you will be familiar with it if you're not yet, but you should go look it up. Um, so the offset value for that is usually, so how that works is basically it has an offset value because it's designed to be utilized with for AC and DC um, systems. So usually has an offset value and offset voltage, and then essentially what you get, whatever you calculate, you have to scale that with the offset. You have to take the offset into account, and depending on how you connect it, it might be you have to take this section minus the offset, or the offset minus this. I usually like it in this configuration because it doesn't go past 2.5 volts, so it goes from 0 to 2.5 volts. So I prefer it in this configuration right here, where you use this particular equation as it becomes valid. So what you have there is basically offset. So first off, you have your VREF, you have your raw ADC value as described in previous sections, and you have your maximum value that your microcontroller actually gives you, which is 4096 if you want to be, specific, 4095, but let's say 4096. So this actually gives you the voltage on the pin itself. But that voltage on the pin, it's important to note that it has to be calculated relative to an offset. So you need to take the offset and say the offset minus that particular voltage you're sensing on the microcontroller pin. Then after that, then that value is actually what represents the current, right? And then that you have to divide by sensitivity in this case. So it's called a sensitivity. So different Hall effect current sensors have different sensitivities. So the next step is basically to calculate it to get the raw ADC value out to multiply it by essentially constant. So in this example, I made an example, assuming it's an STM32 or 12 current sensor, but a 20 amp variety. So the offset value is usually 2.5 volts. The sensitivity is 100 millivolts, so which means it was 0.1. The VREF in this case is 3.3 volts, and here it's 4096, 2 to the power of ADC raised. Of course, this is 12 bits in this case, that's why it's 4096 or 4095. Yeah. All right. So in the end, you have I actual, which is going to be 25. So when you calculate everything out, multiply everything out, you have 25 minus the raw ADC value multiplied by that. So how you would essentially implement this in the code is you just copy that and go to the next line. So you just say I actual equals to that. Just do this. So this is how you define it in the code. In the case of using a Hall effect current sensor, it should be noted that of course you have to look at the data sheet of whatever sensor you're using. The offset valve, if you supply with 5 volts, is usually 2.5, like half of 5 volts basically. And the sensitivity dependent, as far as I know, 20 amps is like 100 millivolts, 30 amps is 0.66 millivolts, so this would have to be 0.066. So you need to get those values and understand your VREF as well and your maximum resolution, that all these values, and you plug that into this equation and then you get that, and this is what you use for your code. Of course, you might want to play around with it because Hall effect current sensors have a tendency. They have certain tendencies. They have certain issues, and they don't always match. Because they're very prone to be affected by magnetic fields. So if you put them next to an inductor, well, you sort of get what you pay for in that case. So yeah, yeah, it's something to just take into account using Hall effect current sensors. But for high current situations, they're an absolute necessity. So yeah, that's that. So that's about it. I just sort of wanted to touch on that because it's important to know that not everyone uses shunts, as I'm using in this case. Oh my gosh, I left the system on. Let me just turn it off. All right. So it's just important to note that yeah, to just keep that in take that into account in your systems. All right. Let me just go back and just see if I missed anything. I don't think I did. So that's it. That's about it. In terms of comments, obviously the code that will be available in the end, for you to sort of utilize. We'll have comments included in it, to be utilized in your example in your various applications. We'll have comments in it, so you should give that a try, and you should, yeah. But that's about it. I'm still scrolling up and down to see if I missed anything, but I don't think I did. Yeah. All right. So that's about it in this section, and then the next section I will be touching on, sort of, we're touching on what we call average current mode control, because of course in this case I have two sensors, current sensors. One is actually one is actually connected to the inductor, so there's a thing called average current mode control, and I'll be sort of tackling that in the next section. I like to think of that one as a bonus section because I won't be touching on anything sort of theoretical there. It'll be sort of dump suck and practical sort of thing. Just straight into the practical and just going at it with the firmware. All right, that's about it for this section, and I hope it's been helpful. This part, from this point on, you should be able to apply this from everything, from all the previous sections, all the information you've had. Granted, you might not be using a specific nuclear board, but they're all, very similar to one another. I specifically use timers that are available on the other boards, and the equations have variables that you can easily apply to the other boards, frequency, etc., ARR values, etc. And yeah, I hope this has really been helpful to you. And yeah, I'll see you. I'll see you in the next one. Cheers.